Welcome back. Today we're talking about rings. So, what is a ring? Well, it's another mathematical structure similar to a group, but we add a little bit more to it. So, formally, a ring is a set R with two operations, and those operations are addition and multiplication. Normally denoted by plus and a dot, but when we talk about multiplication, we just slam those two symbols together and we get rid of the dot. So it's this set with these two operations such that R plus, taken as a structure, is an abelian group. And it's very important that it's an abelian group, otherwise we lose some of the properties that make a ring nice. Secondly, we have that R with multiplication is associative and closed. Normally we call this either an associative closed structure. That's really wordy, so we just say it's an associative binary operation. And finally, we have the distributive properties. So you might remember this from elementary or middle school, but it essentially says that if we have multiplication with addition on the inside of parentheses, we can just take that and move it to each of them. So a times b plus c is a times b plus a times c. And rings aren't necessarily commutative, so we have to have a right distributive law as well, which is shown on the screen. Let's talk about some special types of rings. So we're going to talk about a few here, and then we'll talk about one more in an upcoming example. So if a ring has what's called a unit, normally denoted 1 when we're talking about rings, that's the identity element, we say that the ring is what's called unital. And not every ring is unital, but if it is, it has the nice property that it has a multiplicative identity. Additionally, another type of ring is that a ring with an inverse element for every non-zero element. So if a ring, if you have an element in a ring and it's not zero and it has an inverse, we call that a field. So a property that it has to have in order to be called a field is also has to be commutative, which we'll talk about when we go through our first example. Now, just note that it doesn't really make sense to talk about inverses unless we have an identity, because what do you actually do when you have an inverse? It has to multiply to equal an identity. So if we don't have an identity, it doesn't make sense to talk about inverses. So let's look at our first example, the integers with addition and multiplication. As we've already seen, the integers with addition is an abelian group. If you haven't seen that yet, check out my last video on groups. So what we have to do now is we have to show that the integers with multiplication is a closed associative operation and that the distributive property holds. So to show that it's closed, there's not really much to go into. We've already seen this through our time in elementary, middle, high school. If I take two integers and multiply them together, I still get an integer out of it. The associative property, we've also seen that. It doesn't matter what order I multiply things in, I still get the same answer. So 2 times 3 times 5, doesn't matter if I do 2 times 3 first and then times 5, or if I do 3 times 5 first and then multiply it by 2. So this shows us that all we have left to do is check to see the distributive property holds. And I'll leave that as an exercise to the viewer. It's not very difficult. We already know how to do it. Now, this ring is also commutative. Now, when we talk about groups, we call these abelian groups. When we talk about rings, we just call them commutative rings. So we don't call these abelian. And that's just because if we take A times B, it's B times A, right? It doesn't matter if we do 3 times 5 or 5 times 3. It's fine. Now, it's also a unital ring. And that's because it has a multiplicative identity. And that multiplicative identity is going to be 1. All right, so examples 2 through 4 are just number systems that we're already familiar with. We have the rational numbers, which are all your standard fractions, 1/2, 3/5, 22/7, and the rational numbers are normally denoted by Q. Next is the real numbers. These are numbers that we're also pretty familiar with. These are numbers that include the rationals, but also include like e and pi, and we denote that by a fancy r. And finally, the complex numbers, which we denote by C, which are all numbers that look like a plus bi, where I is that imaginary number and a and b are real numbers.